All right. So for my talk, I'll be talking to you about the early olfactory system and my feeble attempts at modeling it. I will make it look like this is sort of one cohesive thing, while in reality, I was just sort of, bouncing around, trying things out, and nagging Robert and Erica in the process. Right. So since I think Marco and I are the only people on this course working with insects, with flies specifically, I'll be giving sort of a broader overview and not going into too many details. But when we look at the olfactory system, we probably have to start with the sensory neurons, which in case of the fly are situated on the antennae. Per antenna, you have about 1,500 sensory neurons, each of which expresses a single or two receptors. These receptors respond not to just one odor, but usually sort of a battery of odors, with sort of some preference towards 1, 2, maybe 3 odors. So the olfactory code is degenerate. But the type of sensory neuron is defined by the expression of whatever receptor. Then when we get to the brain, so what you see here in red is what the fly brain looks like, or more precisely the neuropil. So i.e. essentially the bit of the brain without the cell bodies, right? So the cell bodies are in the cortex surrounding the neuropil. The brain is fairly small, obviously, about 1 millimeter across, which amounts to about 0.08 cubic millimeters and contains about 100,000 neurons. The important thing about insect neurons in general, and this is why, one of the reasons why Drosophila is a nice model system for neuroscience, is that the neurons are highly stereotyped. So what you see here is just a selection of the same neuron type captured across different brains. So each of these neurons here was imaged in a separate fly brain and then sort of registered to a common template. And there's thousands of examples like that. And I hope you can appreciate that they all look very much the same. And we have all reason to believe that these neurons are not only morphologically stereotyped, but also functionally stereotyped. Okay, now back to the brain. So if we look again at the early olfactory system, what is happening there is these olfactory receptor neurons, or more precisely their axons, project into the brain, and they terminate in this antennal lobe, which is the insect analog of the olfactory bulb. And it has a very similar organization in the sense that it has these glomeruli, where each glomerulus is the target of one specific type. Again, correlates with the expression of a given olfactory receptor of sensory neurons, right? And add a bit more detail. When we look at the antennal lobe, we find 58 of these glomeruli, again, each of which receives a specific type of sensory neuron, or is the target of a specific sensory type of neuron. There's about 3,000 of them, as I said earlier, falling into 61 types. Then we have inhibitory local neurons, of which there are about 200, falling into 70 types. And then, so there would be sort of input, local computation, and as when it comes to output, we have these projection neurons. They're analog to mitral and tufted cells in mammals, and they come in, broadly speaking, 2 flavors. One is these uniglomerular projection neurons, because they sample only from one glomerulus. And typically, every glomerulus has one or up to 2 types of these uniglomerular projection neurons. And then there's a second type of projection neurons that sample from anything between 2 up to all of the glomeruli. Okay. Now, sort of not just in time, but fortunate timing, and in a sense for this course, as of middle of last year, we have the so-called Hemi brain connectome for a fly brain, and this is produced at Genelia, which is just outside of Washington D.C. And what the people there did, in collaboration with other labs, including ours, is they took a fly brain. You can see the outline in the back, and they took about half of it, slightly more than that, and ran it through an electron microscope, segmented the image data, and then essentially extracted neuromorphologies out of it. And including synapses. And the important thing here is that it includes almost all the entire antennal lobe. There's bits and pieces missing here and there, but the coverage is probably around 90%. In total, the connectome is about 20,000 complete neurons. There's obviously some truncated ones there, where like some of the neuron is outside of the volume. 20 million chemical synapses. There's no gap junctions. And the whole thing is publicly available. So if you want to give it a browse, newprint.genelia.org. published in Shepard al. In 2020. Now, just sort of drive that point home. So we've got all types that we need to model the antennal lobe, which is the receptor neurons that you just saw now, and then we've got the local neurons. And last but not least, we have all the projection neurons. Okay, and then just to sort of show it, once you go to the third order neurons, which show up in just a second, you sort of see this explosion of cell types that are downstream. Okay, so what do we get from this connectome? So we get a full morphology of neurons. This is just one example of one of those projection neurons. We get all its inputs and outputs, i.e. pre and post synapses. So this is what you see in red and in teal. Teal are the inputs, so you can see, this is where this neuron has its dendrites, and it just happens to be a uniglomeralar projection neuron, sort of one nice sort of confined structure. And then this is the axon. And not only do we know where the synapses are, we also know what these synapses connect. And from that, we can extract a JCC matrix like this that essentially represents all the connections in the antennal lobe. So what I did for this course is I essentially, hold on, let's pause this for a second, is I used leaky integrated and fire neurons, so point neurons, specifically these INT-Fire4s. And I essentially took the matrix and translated it into a neuron using NetPyNE. So each neuron is one of those INT-Fire4 neurons. The connections between them, the weights are based on or correlate with a number of synapses between those neurons, more specifically with the fraction, because that sort of turned out to be nice, sort of in the right ballpark. So as an example, say there are 5 synapses between neuron A, from neuron A onto neuron B, and neuron B has 100 synapses in total, then the weight would, in this case, be 0.05, right? For inhibitory connections, like the ones from local neurons, I would just invert the weight. And I actually had to play around with it, so there's a modifier in there. I think I took it ×2 in the end. I sort of fine-tuned it in a way that I wouldn't get too much and not too little activity in the network. And then on top of that, just to sort of provide some input to the network, I have 2 types of net stems. One provides sort of constant background noise of 20 hertz onto these sensory neurons. So these are the sensory neurons, these are the projection neurons, color code is the same, and these are the local neurons. 20 hertz is about what we expect from the literature, these neurons to have as sort of a background firing rate. And then I had a second type of net stem that I activated that had higher, provided higher input, but was only active during sort of stimulation periods. And in terms of the protocol, what I did is I basically had these 150 millisecond windows. The first one is to control, and then I sort of, in sequence, started stimulating individual glomeruli, right? For example, in the first one, just alphabetically, I started with a D glomerulus. So for 50 milliseconds, you drive this glomerulus, and then you give it like a 100 millisecond cooldown, okay? And this is essentially what you see in this video. Oops. There you go. So you can see sort of this background. It's an artsy thing, so it's not like 100% accurate, right? But essentially, you see this sort of background activity, and then every now and then something pops up more strongly, and this is when I activated the respective glomerulus. All right. So in terms of output, these are the raster plots for the first 2,000 seconds of this model. I think I ran it in the end for like six seconds or something. And broken down by type. So you've got the sensory neurons up here. You've got these uniglomerular projection neurons, the multiglomerular projection neurons, and the local neurons. And you can see the background noise kind of nicely works. And then whenever I activate these glomeruli, which essentially comes down to driving these sensory neurons, you can see the activity sort of fizzling out. You can also see, I hope you can appreciate that there's some sort of correlated activity in these UPNs. Again, I mentioned earlier that there's usually 1 to 2 sort of cognate uniglomerular projection neurons for every glomerulus. So essentially, this is what I expect. There's also some interesting structure and activity for the multiglomerular projection neurons and these local neurons. They're a bit sort of a black box, so I don't really know what to expect. And this is kind of part of the reasons why I'm interested in modeling this, because if you think about sort of experimentally addressing what every one of those 3,000 odd neurons are doing, you'll be spending the rest of your career at them, and a couple other people's careers as well. So essentially, I'm actually most interested in these neurons. But to sort of prove this model sort of does do stuff that's sensible, the UPNs, where we have an intuition of what they should be doing, are a nice benchmark or landmark. And then the last thing I want to point out is that I don't know whether you can see this through Google, through Meet, but if you squint a little, you can see that there's sort of this, the signal gets dimmer or lighter, so there's less spikes sort of around with a slight delay to the stimulation, which to me is sort of an indication. It's hard to quantify because the background activity is not high to begin with, especially in the other types, but I think this is sort of signs of lateral inhibition. And just to sort of show this in a more quantifiable way, so this is essentially a matrix that tells me what happens if I activate glomerulus D or DA1 or DA2 and so on and so forth. And then in this case, the readout is the activity of these uniglomerular projection units. Again, a nice benchmark. And all of this makes sense, which is nice. So whatever, control, nothing happens. And then when you activate this D glomerulus, then the cognate D UPN starts firing, right? But hardly any of the others respond. So that's all nice and good. At the end of the day, this is a very complex model, and I'll have to A, improve it, and B, sort of think hard and long about what this is actually telling me, especially when it comes to the other cell types. But one of the things, when you sort of dig down into the details of your model, I don't know whether you've also experienced that. You always sort of have these sort of bumps in the road where things don't quite match what you want, and then or what you expect, and then you sort of need to think about how to improve it, obviously. So one of the things that came up is that the firing rates are way too high. So this is just sort of over the course of a simulation, right? So every one of those bars indicates a simulation, and this is then the response over time and firing rate of those different neurons. Each trace is a single neuron. And I know from literature that, for example, these uniglomerular projection units, they should be firing higher than 200 hertz. So essentially, I need to sort of adjust the model to make sure that they don't. There's a different integrate and fire model that has an refractory period, and I probably need to play around with that. And then last but not least, so one of the other things I looked at in parallel is I made compartment models of these neurons, right? So we have this nice morphology, and we know all the synapses are, so why not use it? And this is just an example of two projection neurons. They have their dendrites in the same place, but receive vastly different numbers of inputs. So one has, whatever, a couple thousand inputs, the other one has a couple hundreds. So presumably they're different in their response profile. So what I did here is I essentially randomly sampled the synapses, the inputs and the dendrites, and activated them and checked whether that combination, could have been 2, 3, 5, 10, 20 synapses, whether those would elicit a postsynaptic action potential. And this is what you see here, right? So top row is this teal projection neuron, bottom row is the red projection neuron. And then if you just focus on the first column for now, so essentially you can see that, activating 5 synapses doesn't really do much, 10 doesn't do much, but as soon as you hit like 15, maybe after 20, then you can sort of reliably elicit a postsynaptic action potential. For the type 2 PNs, I'll just call them type 2 because it's easier, they actually do have names. That starts a bit earlier, so about 10 synapses or 10 plus synapses give you reliably postsynaptic action potentials. Which already proves that I can't treat all weights the same or all sort of numbers of synapse connections, X number of synapse connections the same. This gets even worse if I look at the fraction of inputs, because it turns out that these type 1 PNs are the ones that have lots and lots of synapses. So 20 synapses for them is just 1% of the inputs in total, whereas the same is about 10% for the type 2 PNs, which have in total much less inputs. Bottom line is I'll probably need to look into how to fine-tune those weights and adjust them on an individual basis, basically for each neuron, figure out what does 5 synapses actually mean for that neuron. And with that, I'm already at the end of my talk. I'd like to thank Eric and Robert for allowing me to nag them, and Salvador and Joe for organizing the thing, inviting me, and doing the demos. And at that point, I'm happy to take questions.
Very nice presentation. Beautiful.
Very nice. I had a question, Philip. This is Erica here.
I know.
Really great presentation. I really liked the graphics. Really, really wonderful. The videos and stuff, especially. So I just had a question. You made this network with the integrate and fire neurons, and then you also showed us, the beginnings of sort of more detailed compartmental neuron, compartmental model neurons that you would I assume, hope to use in a potentially more detailed version of the model where you use the integrated fire neurons. Is there any question or types of information that you might be able to glean even from or that you're hoping to glean just from the sort of simplified model using the integrate and fire type neurons? Or do you think that it'll be necessary to kind of have the more detailed compartmental models to get at the kinds of questions that you're interested in?
That's a good question. So the thing that the model already recapitulates are the things that sort of the motives that you can already see by just staring at the matrix, right? Like basically strong connections. So, there's already stuff there because, at some point that matrix gets so complex that you can't really see everything at once. So even pointing out the obvious things might be useful here. Even if the model only points out the obvious things, this would be useful. I guess I think I showed you this, right, when we had our first chat. I'm actually interested in some very specific responses of some of these PNs, right? So we know that some of these respond physically, some respond tonically, and presumably encode concentration versus the change in odor, right? And I think for that, I probably need to have some sort of more fine-grained control. But at the end of the day, if I can come up with an hypothesis and then somebody proves it experimentally,
Yeah, absolutely. Yeah, great. No, it was interesting to see some of the network connectivity stuff emerge even from the simpler version. So very cool. Nice work. Really great presentation.
Thank you. Any more questions? No. Just stop sharing.